Hi, this is Steve. Welcome to my lecture series on non-Euclidean geometry. This first lecture is just an overview. We're going to talk a little bit about what non-Euclidean geometry is and how it arose from the parallel postulate, or at least the negation of the parallel postulate. Then subsequent lessons will cover hyperbolic geometry and elliptic geometry. The lecture series is based on a book that I wrote, or at least one section of a book that I wrote. That's free to download, or at least the electronic version is, and I'll put that link in the information to this video. As I noted, this particular lecture series is on the topic of non-Euclidean geometry, and it's based on Euclidean geometry with some modifications which lead to different theorems. If you're not familiar with Euclidean geometry, or if you've forgotten it, I have yet another book that I've written called Shape Up and Solve It, Learn Geometry Through Puzzles. And there's a brief, I don't know, maybe 30-page introduction to Euclidean geometry at the beginning of that. So you may want to have a look at that. The electronic version of that book is free, and here's the link. But again, I'll put the link in the information to this video. The focus in this series is on hyperbolic and elliptic geometry, which are defined by modifying the parallel postulate of Euclidean geometry, which I'll talk about in a minute. There's also something called affine geometry, which I'm not going to cover in this video series, but I'll just mention it here briefly. Affine geometry, or non-metric geometry, is what remains of Euclidean geometry when we ignore or forget or not use the notions of a distance and of angle. So it's kind of really pared down to a very small amount of axioms, but it's another type of geometry which we're not going to cover here. So as I say, I'll just mention it once here, and then we'll focus on hyperbolic and elliptic geometry. So let's talk about the parallel postulate. This is kind of at the heart of where these non-Euclidean geometries branched off from Euclidean geometry. For a long time, from the time of Euclid really, mathematicians tried to prove the parallel postulate using these other four postulates from Euclid, and they never were able to. There was a lot of false attempts, but they were never able to prove the parallel postulate. And it turns out that it's not necessary, or at least not necessary as stated, and you can actually do some variations on it, which I'm going to talk to you about here. So Euclid's fifth postulate, also known as the parallel postulate, is synonymous with Playfair's postulate. This postulate, which applies to Euclidean geometry, asserts that in a plane for a given line L, I have a picture here of it, and a point A, not on L, excuse me, there exists exactly one line passing through A does not intersect L. So it's hopefully kind of common sense, or at least common notion, that you would have a line going through A parallel to L, and there's only one such line. That's the case for Euclidean geometry. In hyperbolic geometry, on the other hand, there exist an infinite number of lines through A that do not intersect L. And we'll see what that looks like. I have a couple of rough pictures on the next few slides, but it's basically bent space where you have the line coming this way and then going out like that. And so there's an infinite number of lines that go through A and don't intersect L in hyperbolic geometry. And in elliptic geometry, every line through A does intersect L, so it kind of bends in the opposite direction. So let me show you what that looks like at a high level. We'll get into a lot more detail in latter lectures, but let's just kind of get a general idea on the next couple of slides. So these are the three cases I mentioned before. In Euclidean geometry, we have these two parallel lines, And no matter where you draw a perpendicular, it's going to be the same distance between the points on either end, between this point and this point. We could draw it here, we could draw it here. In hyperbolic geometry, these are two parallel lines, and you can see here that we have the perpendicular to them. But if we move it out here, the distance between the two lines gets greater as you move further away in either direction. And for elliptic geometry, again, we draw a perpendicular to these two parallel lines in quote. Of course, they don't look parallel, but they are in elliptic geometry. And eventually they meet, and they get closer and closer as you get further away from this middle point, and they eventually meet. I'm just repeating here in words what I said in the previous slide. We have Euclidean geometry, which, as we know, the parallel lines don't intersect and the distance between them, if we draw a perpendicular, remains the same. In hyperbolic geometry, the lines, again, what are parallel lines, or they actually call them ultra-parallels, they curve away from each other, so as you move further and further away from some center perpendicular, you get the distance gets bigger and bigger, and then you have just the opposite in elliptic geometry. The parallel lines get closer and closer as you go further and further away from some middle point. Yeah, so here's another representation that maybe gives a little bit of background into why the lines curve away or towards each other. In Euclidean geometry, you just have a flat plane, and that's known as having zero curvature. In elliptic geometry, there's what's called positive curvature, and it's one example of elliptic geometry is a sphere. So if you draw a line on a sphere, as I'm showing here, the lines eventually touch each other and intersect. And triangles have the sum of the angles of a triangle are greater than 180 degrees. In Euclidean, as we know, the sum of the angles in a triangle is 180. And then in hyperbolic, you kind of have this curve going outward. And you can see here, if you draw lines here, they get further and further away from each other from some common point. And the sum of the angles of a triangle is less than 180 in hyperbolic geometry. Okay, and then just some notation on, I'll try to stick to this. I won't be perfect, but I'll try to stick to this in the different diagrams in the future lessons. So you may want to refer back to this as needed, or I'll try to remind you also when I get to the different figures. So geometric points, I'll use capital letters to indicate those, like capital A, capital B, and you already saw that in the one figure I had with the line and the point A. Angles are indicated by lowercase italics. I'll usually use Greek letters like alpha and beta, delta, gamma. Lines are usually represented by script letters like L, M, N. A small square at a vertex of a polygon indicates a right angle. That's commonly done in high school geometry books and all geometry, really. You just kind of have a right angle, a square. Figures are not always drawn to scale. This kind of comes into play a lot with the way the lines intersect. I may not draw the curves. It's kind of hard to draw them as curves all the time. So I may draw them as straight lines and explain that they're actually curving in hyperbolic or elliptic space. And then given 2 points, we use the notation AB to indicate the line AB, sometimes the line segment AB, just going between A and B, and then even in some cases the distance between A and B. And I'll try to explain the context. If it's not obvious, I'll try to explain that. So that's some common notation I'll be using in the future lessons.